The coldest place in the known universe isn't in deep space. It's inside a computer. Empty space sits at about 2.7 degrees above absolute zero. The chip inside a quantum computer is held more than 100 times colder than that. Why? Because the qubits inside aren't like anything in your laptop. To understand them, we have to go back to the coldest laboratory of 1911. On April 8, 1911, in Leiden, Heike Kamerlingh Onnes cooled a wire of solid mercury in liquid helium and watched its electrical resistance completely vanish. In his notebook, he wrote, "Mercury, practically zero." He had discovered superconductivity, electric current flowing without any resistance at all. Below 4.2 degrees above absolute zero, Mercury's electrons stop jostling like a crowd and start moving in lockstep, like one single quantum object. Half a century later, in 1962, a 22-year-old student named Brian Josephson predicted something stranger. This supercurrent could tunnel straight through a thin insulating wall. That sandwich, superconductor, barrier, superconductor, is called a Josephson junction. It is the heart of almost every superconducting quantum computer today. Here's the trick. Build a tiny superconducting circuit around a junction, and it stops behaving like wiring. It behaves like a single, giant, artificial atom. A real atom has energy levels. So does this circuit. The junction spaces those levels unevenly. So you can talk to the bottom two, and only the bottom two. Level 0 and Level 1. You address them with microwave pulses, tuned near 5 billion oscillations per second. That is a superconducting qubit. In 1999, at NEC in Japan, Nakamura, Pashkin, and Tsai controlled one for the very first time. Its quantum state survived just a few billionths of a second. A few nanoseconds. Why so fragile? Because this atom is artificial, and its energy gap is astonishingly small. The jump between level 0 and level 1 carries about as much energy as heat gives a particle at 1/4 of a degree above absolute zero. Room temperature is more than 1,000 times hotter than that. To a qubit, your living room is a hurricane of thermal noise, flipping it at random. Even deep space, at 2.7 degrees, glows 10 times too hot. To hear one quantum note, you must silence the universe around it. That is the job of the dilution refrigerator. The golden chandelier in every photo. It isn't decoration. Every layer down is a colder stage. At the bottom, helium-3 atoms dissolve into liquid helium-4, and each atom that crosses over absorbs a little heat. Evaporation, but near absolute zero. 10 to 15 thousandths of a degree. The chip hangs there in vacuum, in the dark, colder than anywhere in deep space. And the cold pays off. With better circuits and better fridges, coherence grew from nanoseconds in 1999 to 100 microseconds and beyond, tens of thousands of times longer. So a quantum computer isn't cold because it's high-tech. It's cold because it's quiet. The refrigerator isn't the machine's engine. It's the machine's silence.